In this video, we're going to look at finding explicit formulas for recurrence relations. We're going to find explicit formulas for recurrence relations. First, we have to recall some sums. Recall that if you have a summation, say I equals 0 to n, of say Ri, this is equal to R to the n plus 1 minus 1 over R minus 1 to the n. So, for example, if you have the summation of 2 to the I equals 0 to 3, let's say, that sum is going to be equal to 2. Notice our R value here is 2. 2 to the n plus 1. Since n is 3, this is going to be 3 plus 1 minus 1 over 2 minus 1. That's going to be the sum of this in an explicit form. And now, of course, what would that be? That would be 2 to the 4th minus 1 over 1. And 2 to the 4th, of course, is 16 minus 1. And that's 15. And we could check this, of course. If we actually did this sum over here, if we looked at the individual terms, we would have 2 to the 0 plus 2 to the 1st plus 2 to the 2nd plus 2 to the 3rd. And that's equal to 1 plus 2 plus 4 plus 8. And this is 14, 15. So that checks out. Now, suppose that your sum doesn't go from I equals 0 to n, but goes to maybe, say, n minus 1. Then what you do over here, you reduce this by 1. So, for example, if you have, so this is kind of the main form. And so you can adjust that. If you have I equals 0, say to n minus 1, then you just reduce this by 1. So instead of being n plus 1, that's just n. And that would be the case. Or if you, or let's say you have summation I equals 0 to n minus 3. Again, go back to this one here. So instead of n, you have n minus 3. So you have 3 less. You have to reduce this by 3. That would give you R to the n minus 2 minus 1 R minus 1. Now, what if your sum does not begin at 0? Now, if you've had calculus, there are ways to do it by adjusting the bounds and so forth, but probably the simplest way is just to subtract the missing terms. And let me give an example. So suppose that you want to find this sum here, Ri. Again, go back to your original form up here. And again, so that goes to the n, we use that original form. And so that's going to be equal to Rn plus 1 minus 1 over R minus 1. Now, except this sum here represents all the terms from 0 to n, but we don't have all those terms from 0 to n. We just have the terms from 3 to n. So we're going to have to subtract the missing terms. So that would be, notice 0 isn't here, so that means R0 is not here, so we have to subtract that. And I1 is not here, so we have to subtract that. I equal 2 is not here, so we have to subtract that. So again, we're subtracting the missing terms from this sum. So again, just to review, this sum right here represents all the terms from 0 to n. But since we don't have all the terms from 0 to n, we don't include R to the 0 is not here, so we have to subtract it. R to the 1, subtract it. R2, subtract it. So mainly subtract missing terms. Now we're going to use this when we try to find explicit formulas for recurrence relations. So keep these sums in mind. So let's take a look at this example here. Here we have this recurrence relation. AK equals 4, AK minus 1 plus 5. And our initial condition, A0 is equal to 2. We want to find an explicit formula for that. And that is, we want to find an explicit formula that we can plug in any n and find out what the term is. And the best way to understand this is we'll go through some examples. And mainly what we want to do is find the pattern. And the best way to do that is just to do a bunch of terms here. So let's do A of 1. So according to our formula here, A of 1 is equal to 4 A of 0 plus 5. And what does that mean? 4 times 2 plus 5, which is A0 was 2, so we plug that in. Now, for a lot of these, we don't want to simplify them completely. We want to kind of keep them separated a little bit so we can see the pattern. So let's leave that there. And let's go to A2. According to our formula, A2 would be 4A1 plus 5 And now A1 was this. So we're going to put in A1 into here. So again, this was 4, and this was the A1 plus our 5. And again, you might want to multiply that just a little bit just to kind of see what's happening. 4 squared plus 4 to the 5th plus 5, something like that. And let's go to the next one. A3 is 4A2 plus 5. So 4. Now let's put in A2. 4 squared 2 plus 4, 5 plus 5. That was A2. But then we still have to add our 5 on. And again, let's just multiply this out. We want to get just a general idea what's going on. Cubed times 2 plus 4 squared times 5 plus 4 times 5 plus 5. And we probably can see the pattern at this point, but let's do just one more. A4 is going to be 4A3 plus 5. And so we're going to put 4 times A3 is going to be this. Oh, by the way, I forgot this 5. There's an extra 5 right here. It's easy to miss that. This is 4A3. A3 was this plus our 5. Now when we distribute the 4, now we can maybe see the pattern here. In fact, let's notice what we have here. We have for n equal 4, we have 4 to the 4th times 2, then 4 cubed, 4 squared, 4 to the 1st. And you can think of this as there being a 4 to the 0 here. So let's actually write that in. It'll kind of more explicitly see what's happening. Like that. And then let's factor out this 5. We can't factor this 2 out, but we can factor out the 5. And we can say this is going to be 4 cubed plus 4 squared plus 4 to the 1st, 4 to the 0 times 5. So now let's see what we have here. So now our guess at the general explicit formula is going to be something like this. Just observe several things. Notice that if we have a 4 here, then we have a 4 in this exponent. And whereas back here, when we had a 3, we had a 3 in this exponent. So that's kind of the pattern. So we have, so that if we have 8 to the n, whatever that n is there, this first term over here will be 4 to the n times 2. And then notice what we have over here. This starts at n minus 1, because here we had a 4 and this was a 3. So that's going to be 4 to the n minus 1 plus 4 to the n minus 2, all the way down to 4 to the 0 times 5. So again, the way we picked n minus 1 was to note up here, whatever number this one was, this was 1 less. Then this was 2 less, and 3 less, and 4 less, etc. And that's what was multiplied by our 5. So this seemed to be the general pattern. But now we can simplify this a little bit more by using the sums we talked about a minute ago. So notice what this is. This is a summation of 4 to the I, let's say, from I equals 0 to I equals n plus 1. Excuse me, that's I minus 1. I minus 1. So from I equals 0 to n minus 1. And so again, according to what we said previously, using our sums, our normal one was r to the I from I equals 0 to n was equal to rn plus 1. We said if we reduce this by 1, so in other words, we have n minus 1, we have to reduce this by 1, make that n. So this is going to be equal to r to the n minus 1 over r minus 1, which in our case is going to be 4 to the n minus 1. And then 4 minus 1 here is going to be 3. And that's all times 5. So let's write this out just a little bit better. We have a to the n is equal to 4 to the n times 2. That's this part here. And so we have this equation right here. So again, all I did was took this 4n minus 1 over 3 times 5. And that's our answer. Now you could, it would be helpful to reduce this more if you're able to. So let's actually go one step farther here. So let's multiply this 5 out. So here we're going to have 4n times 5/5 minus, and this is going to give us a 5/3 here. And then we can factor out the 4n, can't we? And then we put these two numbers together, that would be 11/3. And that's our answer. And notice the important thing about this is, let's say you wanted to find A 100. If you had to use a formula, you would have to do 100 steps. You'd have to go through A1, A2, A3, just like we did here, all the way up to A100. But here, with our explicit formula, this is our explicit formula. You can just put, let's say, 100 into here and get your answer.